Welcome to another video explaining the universe using the particle model. Today's video is on the AC voltage and current versus pulsating DC, which contains an AC signal, and a little bit about math versus physics. Now here's an example of a circuit from YouTube. It's a video, and it shows an AC power source with ground, and on the positive cycle the current flows this way, and on a negative cycle the current flows the other way. And this is the graph of current in this case. And this zero line right through the middle of the sine wave is reference to ground. And on the positive cycle, it goes up to a peak, back to zero. And then when it goes the other way, it has a negative value going back to a minus peak and back. That's basically alternating current, is to have current alternate go this way and then go that way, and it's represented by a value, plus and minus value. But let's talk about the value of this. If you look at a DC circuit, this is just arbitrary DC circuit, and you've got DC current flowing and it's steady state out of a battery. Steady state, 6 milliamps continuous. But the AC signal, that is if AC current flowing as it goes positive and then negative, what's the average value of this? The pluses match the minus, it's zero. How do they deal with the fact that the average value of a sine wave, whether it's voltage or current, is actually zero? Well, there's another video. It's a SlideShare video showing a similar circuit, and in this case there's a 12 volt peak and a 6 milliamp peak. That's where I got that number. And he's taking these individual points, and he's going to calculate the value of the current, in particular voltage and current, and see how they add up. And of course I just explained what they would do, and sure enough, these are the values he gets every 36 degrees. He gets positive values, then on the other cycle he gets the same negative values. You add them up, you get zero. Same thing with current. That isn't helping getting a value for AC. So I say, well, let's do it a little bit differently. Let's not use voltage alone, current alone. Let's go to power. And you multiply voltage times current, you get power. In this case, volts times milliamps gives you milliwatts. And when you multiply these two together, you get these numbers. But when you multiply these two together, a minus times a minus gives you a plus. Now I get a value. So now I have a way to do that, to get an average value of an AC current, which is not zero. Okay, but now what is really alternating in this case? Is the current direction alternating, or is the value alternating? See, it's kind of doing two things. Clearly the direction is alternating. The value, why is the value changing here? Well, you got a plus peak current flowing this way, you got another peak current flowing that way. Why is that value automatically negative? And this is part of the problem with the math. Well, again, they use power, and so they multiply volt times current, and everything comes up positive. A positive voltage times a positive current gives you a positive number, and you take a negative voltage times a negative current, you get a positive number. And when they average that out, you get 0.707 times the peak. In this case, the peak here is A and minus A. That's how they come up with it. If you look at direction, you don't have to worry about negative values, because if it's direction and you have a positive, in the case of a particle model, you have a certain number of G1s flowing here, then you have a peak number, and then another back to this one, and then you don't have a negative peak. I've labeled this positive. This goes clockwise, this goes counterclockwise, and this is a positive number. You don't even have to worry about this, because even if you flip this up and look at it the same way, all you have to do is look at the half wave and do the calculation on the half wave, you get the same number. Don't have to worry about that when you just worry about direction. But they've got direction, and what do? They multiply -1 times a -1. It gives you a +1. And that has a little bit of problem in terms of math. And the way you can see this is using the number line. There's a number line from 0 to +10, other direction from 0, -1 to -10. And you can add, and you can add with it, you can subtract with it. But let's see what happens. This adding says take the number 2 and add to it, and you get 4. Easy. It says take a -2 and add another -2, and you get a -4. Everything's okay. Here you move right, here you move left. Multiplication is a little bit different. It says take 2 and do it 2 times. Take 2 and do it 2 times. 1 time, 2 times is 4. You move right. 2 times 2 is 4. Same thing here. Take a -2, but here I'm saying do it 2 times, not a negative 2 times. Take a -2, do it 2 times, -2, do it twice, you get a -4. Move left. Everything's cool. This is the problem with the math. -2 times a -2 is a +4. Different than that one. What it says is take the -2 and do it -2 times. Now let's get to something simple you can do. I'm going to ask you to take some steps, and I'm going to ask you to go backwards twice. And I want you to do it. I want you to go backwards 2 steps, and I want you to go 2 steps backward a -2 times. How many times did you say I got to go do it a -2 times? You can't do that physically. It doesn't work. Well, Peter Erickson has written a book called The Nature of Negative Numbers. This is his book. By the way, I stole this from my son David, as I usually do. And it's all about negative numbers, this problem in particular. And he even discusses the squirrely negative of a square root of a -1, which we often call imaginary because we don't know what else to do with it. And it is useful in engineering. It's not but using minus times a minus. Oh, one last step I forgot. In this case, you're taking a -2 times, and you get a +4. You actually jump over the 0 line. It's the only one that does that. Goes over the 0 line. Seems crazy. In nature, what I'm trying to point out, there are no negatives in nature. You can't have negative particles or whatever. This comes to mind a little bit about math versus physics. And one of the things that we've seen in the last 80 plus years is that they've tried to unify the Einstein's gravity equation with the one-page equation for the 3 forces in quantum mechanics. If you ever want to get a copy of this, it's easy. Get a copy of this. Go on the internet and Google one-page equation, not one line, one-page equation. And you'll get multiple copies of this. And this one equation is supposed to represent the three forces. That is the nuclear strong, nuclear weak, and electromagnetic. So they got three forces, and they've been trying, they like to get this to match this. And one of the things that's the problem is the math doesn't work. I recently heard on the internet by a statement by Quora that at lower levels, this equation fails. He actually said this equation for the three forces fails at lower levels. Einstein tried to do this until he died, and it didn't work. Engineers and scientists have tried that, and it still does. So what do they do now? String theory is a new theory of gravity. Quantum loop theory is another new theory of gravity. Theoretically, the math of this is being developed to be compatible with that. What's important here? The math comes first. Sorry, my opinion is the other way around. Math has become so strong in physics that it is more important than the physical model. If the equations for all four forces use the same math, then they're unified, and that's been the goal of physicists for 80 plus years. Real physics, physics that I like, is done when a physical model is suggested and the equations developed represent that model. You can see in the equation what it is physically is. That's the way it should be. Math versus physics. Physics first. Make sure the math matches the physics. Okay, the second half of this is about pulsating DC, which is a different form of AC. This is an oscilloscope picture showing the AC signal inside a DC powered circuit as pulsating DC. In other words, you have a DC circuit, in this case from 0 to powered by 12 volts. The operating point here is at 6 volts, and you can increase the current positively, and you can decrease it getting less, but still a positive number. So there's no negatives here. And then this is positive, and this is positive. It went down, but it's not negative. That's called a pulsating DC. You can conceive of this as the number of G1s flowing. I typically use the ratio of 10 G1s to make 1 volt, so this would be 60 G1s flowing. Then the circuit increases it so that 110 are flowing, then 10, then 60, and so on. Pulsating DC inside a circuit. And here's a 3-volt FM transmitter circuit. I use 12, but current flows only in one direction. Current doesn't go this way. G1 particles go this way. Electrons go this way. And they just go steady. And this is the point that the oscilloscope would be looking at as a pulsating DC, which represents an AC circuit. In this case, your voice. This link actually is instructions on how to build this such that when you talk into this and you send out an FM signal that is modulated by your voice, that FM signal, if you're close enough to the radio, will pick up and you'll hear your voice coming out of the radio. It's supposed to be a working circuit. Okay, but here we got pulsating DC, and it's sent to the antenna goes through the capacitor and blocks the DC portion, the direct current portion of that, and that signal goes out into the air to the radio. This is a point I've made before, but I'm going to make it again. G1 particles flow here, come from the battery, flow here, flow here, flow there. G1 particles are part of the FM stream. This is like an electromagnetic wave, only the G1 particles start here, get modulated here to the antenna, they go through the air, and they're received by the radio. G1 start here, and they end up in your radio. One continuous stream looking like either pulsating DC here or another version out there in space. And this is what I'm going to show. Inside the circuit, this is just a repeat of what I said. You got pulsating DC, but when you go through the capacitor, you clip this off. And so now when you get out here, now I'm showing the particle model stream where you have 0 in the valley, 0 particles, and a peak here. What's the average of this signal? This is easy. You take this part, the positive part, put it here, take this positive part, put it here. The average value of this is 6 volts. That's what it is, not 0.707. Even though they'll tell you when you look at the scope and you're in class, they'll tell you that the average value of this is 0.707 of this peak. The average value is 6. Here, what's the average value? Well, now you've clipped off the DC, so you're going from 0 volts to 10 volts, which is 100, a peak of 100 G1s and a valley of this. And what's the average of this? Right through the middle. It's not 0.707 of the peak. It's the average value, which here is 50. Well, this is just another one. I'm just repeating it. I'm not sure why I put it there, but there it is. It's the same thing. The conclusion: alternating voltage and current means alternating direction, not alternating value, because there are no negative G1s flowing through the circuit. They're all, you either have them, they're either there at the peak as 100, or there's none. But there's never a negative number of G1s flowing. TPM particles never have a negative number of values, is what I meant to say. A volume of space can have many particles, can have only a few, can have many, a few, or even have none. But there will never be a minus number of particles. My name is Bob D. Hilster, and I am your particle model guru. Tune in next time when I'll explain more of the universe using the particle model. Thank you for your attention.